polynomial function. Now you have this. I want to spend some time looking at this. Look, what you see up here in these examples, they're all polynomials. A power function is like this. It's just a single term. So x to the power 2, x to the power 4, x cubed, and so forth. And we classify them by even or odd. Any kind of polynomials, either even or odd. Basically, the degree can either be an even degree or odd degree. If it's a power function, then it's just the exponent. So these are both even degree because it's exponent, degree 2 and degree 4 terms. The 7 is irrelevant. And here these are both odd because they're degree 1, degree 3. Okay? And the point is, here's your basic in behavior for any polynomial function. If it's even, it would be like a parabola and open up on both sides. Listen, this speaks nothing to what it looks like in the middle. If it's a power function that's even, it'll be like this, like a parabola. But if it's not, if it's some polynomial, it'll be connected some other weird way. Same thing with this. If it's like x cubed, x to the power 5, and then like that, it'll just go through the origin like that. But anything else, it'll look something like this probably, and have various maxes and mins in between. Now, and then those are your two basic shapes, basic behaviors. And if you put a negative sign in front of them, they flip upside down, and there you go. There's your 4 possibilities for in behavior of any polynomial. Okay. Now, I'm going to start getting you used to basically classifying any polynomial the way I just described. And so if it's a polynomial that's simplified, it's easy. It's just the biggest term. That's all you care about. And so this is an even one because it's degree 4. This is a degree 5 polynomial. The whole thing is degree 5 because the biggest exponent is 5. Okay? Now, these, it gets more complicated in terms of how to figure out. Basically, here, watch. This one is degree 4, like I just said. Part B, we can figure out the degree without doing any algebra. But I want to show you how the algebra would look if you simplified it. First of all, this, we just did that. We did binomial theorem, didn't we? Because it's just x plus 1, the numbers I'm going to use are straight from Pascal's triangle. I think that is the expansion. If you did x plus 1 cubed, you get that answer. And we'll put the x out in front. This one, by the way, Pascal's triangle is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So just for the record, if I ask you what is x plus 1 to the power 4, the answer is 1x to the power 4, 4x cubed, 6x squared, 4x plus 1. Of course, if it's not just x plus 1, it's more complicated. The part where you do n choose j would make it so it's not just these numbers. But for this example, that doesn't affect it. Anyway, back to this. Because it's squared, you actually use this. But there's actually a formula for that, right? A squared plus 2ab plus b squared, if you're just squaring a binomial. No, I meant for this to be a 3. Make it a little more interesting. So what's going to be the first term? X cubed squared is x to the power 6, right? Use your exponent rules. And if you do 2ab, you get 1x cubed doubled is 2x cubed, the middle term. And then plus 1, because 1 squared is 1. Now, I think that's about all I'm going to do. I'll do one more thing, actually. If I multiply this by x, then this one becomes x to the power 4 plus 3x cubed plus 3x squared plus x, right? All this is unnecessary work because all I'm trying to figure out is the degree of this polynomial. And so these are all the same polynomial, by the way. I'm just trying to simplify it. If I wanted to finish this job, you'd have to multiply each of these times each of these, which would be 12 different multiplications. And then you combine. If I was going to do that, which I'm not going to do, the way I recommend is make a table. And I guess the way I set it up, I do the 4 terms across the top and 3 terms across the side, and do it all in multiplication. It gets it very well organized, and your like terms are easy to identify. But regardless, I'm not going to do any of this multiplication because all they really cared about was the term with the biggest degree. So I don't care about any of those. I'm not going to multiply any of that. All I care about is this term times that term. And what does it give me? X to the power 10. Not 10, but x to the power 10. By the way, assuming there's no terms missing, how many terms would be in the entire expansion of this? 11. If j went from 0 to 10, you'd have 11 terms, right? Of course, this isn't a binomial to a power. It's more complicated than that. But still, if it's a degree 10 polynomial, there could be 11 terms. There might be fewer, but there could be 11. And once again, though, all we cared about was the first term, which tells me this polynomial is a degree 10 polynomial. Now, look back to the original. If you want to figure that out just by looking at this, you don't need to do any of this. All you need to do is basically ignore the constants and just do your exponent rules. In other words, watch. This really is just x cubed, right? This really is just x to the power of 6. And when you add exponents, you get x to the power of 10, and there you go. Done. It's a degree 10 polynomial. Okay? So let me go back to our table. And I'm saying you should be able to look at a polynomial and identify the degree and figure out whether it's positive or negative, because as soon as you know that, you know what kind of basic shape you're dealing with. That's the point. So look at these again. Look at these examples. This one's degree 4, like we said. What is the degree of this second one? Also 4, because you basically add exponents. The bottom one? Because it's 1 plus 3 plus 2 is 6, which means these are all even polynomials. The degrees are even. This one's degree what? 5. The biggest exponent was 5. The next one is degree also. And the bottom one? Also 5, actually, for a different reason. And so, once again, they're all odd degree, which means they look like this. Now, look over here about figuring out the sign. Sometimes it's obvious. Obviously, this has, and you look at the sign of the biggest term still. This one's positive, of course. This one's not obviously positive. I mean, in other words, you have to think about it, because it's negative there, but it's to an even power. That's why it's positive, right? Whereas you come down here, you have a negative, but this time it's odd power, so that's how you know it's a negative. And so, like I said, it can get tricky. Here, obviously, it's just all positives and negative sign stuck out in front. But it could be more complicated. If they put negative sign here, it's actually still negative, but if I take away one of them, it ends up being positive. So just be aware of that, because if the sign is wrong, then you're going to get the thing going up when it should be down, or down when it should be up, and you'll be wrong. All right, a little preview of that issue of figuring out the degree of a polynomial. For now, we're not dealing with polynomials, though. We're just dealing with power functions. So look at this. We're just going to graph these. Be quick. So here. First of all, I want to make a table for this one. Our normal numbers. What's the parent function? X to the power 6. First of all, what is 0 to the power 6? And I did that first period. Listen, let me write this down. We did spend all our time on exponentials. I can't even write. 6 to the power 0 is 1. That's true. But 0 to the power 6 is 0. What about if I plug in 1? 1, once again, be careful. 6 to the power 1 would be 6, but we're not doing that. We're doing 1 to the power 6, which is 1. 1 times 1 times 1 times 1 times 1 is 1. What about negative 1 to the power 6? Also positive 1. So like I said, we're doing power functions here, which are not the same at all as exponential functions. And then what's 2 to the power 6? 64, and then also 64 here. Be quiet. And then take half of all those y values, and you get, well, 32, 1/2, 0, 1/2, and 32. Now we plot these points. So it goes through the origin, and it goes to a point halfway above the x-axis. Now watch this. Those points are accurate. If a person did all that correctly and then drew this, I would take off a lot of points. Why? Exactly. At 2, it will cross this line, x equals 2, but not there. And so, and I'm serious about this. You know, I want you to use these 5 points, even if you can't plot them, they should guide how you graph each line. It's going to hit the line x equals 2 way up there off the screen, right? So it should be very steep like that. And you should realize that. So that's how the graph should look. Something like that. I gotta fix that. That's not good. Alright, see if I can do this. That'll do. Okay. Alright, now let's go ahead and fill in the blanks. Domain and range are easy, obviously. One thing about the domain, though, you know, look, let me put it this way. Is that a vertical asymptote there? No, of course not. We just said it's going to cross that line at 2, right? And when you get to 3, it's going to cross 3 eventually. It's just very, very steep. My point is, someone glances at this and they'll say the domain is from -2 to 2, which is obviously not true, but it's a common mistake. Now, the range. Is it the non-negatives or is it the positives? The non-negatives. It's the positives and 0. So write it as such. What next? Intercepts, that's easy. They'll get more complicated, but with the power functions, they're always easy. In this case, they're both the origin, right? All right, in behavior, two different notations that you need to be able to use. We just call these behavior statements. So as you go to the right, the function values go on to infinity. And then as you go to the left, if you're talking about in behavior, you're talking about as x goes to infinity or negative infinity. Just for the record, if we're talking about in behavior is also known as long-run behavior. Also, it would be short-run behavior, which would be talking about as you approach some number. Okay? We're not doing that right now. Now, what goes here? Also infinity. Because it's even, it goes the same in both directions. It goes up as you go left or right. Now, you should be able to write it that way, or using limit statements. So here, write down the corresponding limit statements. That's LIM for limit, just cursive. The limit as x goes to infinity of our function, of f of x. You can either put f of x or the equation there. So the limit of f of x as x goes to infinity is, or equals, infinity. So this notation means the exact same thing as this top behavior statement. And then the bottom behavior statement, you just write as the limit as x goes to negative infinity of f of x. And it also equals infinity because it's an even function. So listen, I don't care which notation you use, except you're expected to be able to use both. So sometimes you'll be required to use one or the other. So any given problem, do it one way or the other. Unless it's expected to be a certain way. Continuous, yes, of course, is continuous. Just for the record, any polynomial function will always be continuous. There'll be no gaps, no holes, nothing like that. Rational functions will have asymptotes and holes in them and stuff, but not polynomials. Increasing, decreasing. Listen, you have to remember the point to this. When I ask for increasing and decreasing, I mean over what intervals are they increasing and decreasing? So, Christian, tell me, when is it increasing? And it's decreasing on the other part of the graph, because once again, look at this. When we say this, we say, as x increases, how does it behave? And it was decreasing initially, yes. And then here, it stopped decreasing, started increasing, which, by the way, means that point there is called a relative minimum. Because, once again, you were decreasing, you hit a minimum value, now you're increasing. Okay? One more little thing about this. When we had the assessment over this function stuff, I like that technical term, function stuff, we had blanks for increase and decrease and constant. And what some people did in an example like this is they put 0 there. Your answer can never be a number. It's always an interval. And so that was not valid. It's just never constant. Over no intervals is a constant. Just to emphasize again what an interval means, like if I said the interval from 0 to 1, just that little part of the x-axis, how many numbers are in that interval? Infinite number. All numbers between 0 and 1, infinite number of numbers in that list. If I did from 0 to 100, still infinite number of numbers in that interval. So if I say an interval, you're talking about more numbers than you could ever in your lifetime right now. Okay? So it's not a number. So be careful about that. All right. We're done with that one. Next. We'll make a table again. Same next values. Parent function? Miriam, what's the parent function? No. It's just x to the power 4. So that's our parent, and then the negative 2 is the transformation of that parent. And then that's 0, 1, and 1, and then 16, obviously. And then we're doing negative 2 times that. So the y guys get multiplied by negative 2, so negative 32, negative 2. Or the 3 middle points you can plot. The last point won't fit, but you need to realize that's where it hit, so you don't draw the rest of the graph on. Let's do the end behavior first. Josh, do you want to use behavior statements or limit statements? Okay. So as x goes to infinity, the function value approaches what? Yep. And as you go to the left, it does the same thing because it's an even function. Let's go and do the intervals of increase and decrease. Hayden, when is it increasing? False statement. Michael, when is it increasing? No, he got it. Here, go ahead, Hayden. Good. And then it hits a local maximum or relative maximum. Those terms are interchangeable. Local or relative. And because then it stops increasing and starts decreasing. Right? Okay? And listen, you got to be careful with this because in these two different parts of the problem, we're looking at two different ways. In other words, here we said, okay, as you go to the right, it decreases, and as you go to the left, it decreases. We said it decreases in both directions, which is not how you look at it when you write your intervals of increase and decrease. In this case, it's always as you progress from left to right. Okay, so like I said, it's not the same perspective, if you will. All right, one more. This time I'm just going to sketch it real quick. We're not going to make a table. All the tables I've been doing were totally optional. You just have to get the graph right, okay? And so if it gets weird, use the table to help you. But otherwise, you don't need to. All right, so it's going to go through the origin. And then what's 1 to the power 7? 1, not 7, but 1. Tripled is 3. So there's that point. And what's 2 to the power 7? Come on, 2 to the power 7, 128. Tripled is bigger. Same thing, don't hit that line. And then on the other side, negative 1 to the power 7 is negative 1, right? Tripled is negative 3. What just happened? I just lost it. Come on. I have control again. By the way, just one thing about the shape of an odd function like this. This one's kind of steep, but it's always going to have an inflection point in there like that, where like it was curving one way, it curves the other way. It's just kind of hard to see here. All right, let's do the behavior statements as limit statements this time. So here, what do I put? And when I write the limit statement for the other direction, it'll be negative infinity because it's odd, so of course it's going the opposite direction. Although one thing I forgot I was going to emphasize with these limit statements is watch. You know, we've done things other than power forms. We did exponentials, for instance, and those had asymptotes. So like here, you would say the limit as x goes to negative infinity is, let's say, 0 in this case. Does that mean the function value is 0 sometime? No. It means it's approaching 0. I'm just saying that equal sign we put there, it means the limit equals that number, or infinity. Which you can't equal infinity anyway. But that's what you're approaching. It's always, the limit is what you're approaching. Now, increase and decrease. Then what do I put for that? For increase? No, more than that. It's actually always increasing.
Oh, yeah.
All right. One more. All right. That's the wrong one. Here. Look at this. This isn't on your notes. Just look for a second. I just want you to recognize the parent function here is x to the power 5. Shifted which way? Right? 3? Okay? And so technically this problem is in the next section, but it's really just power functions shifted. So I want you to do the first part of that homework as well.